Hello, and welcome to this recorded learning module for designers targeting Xilinx's programmable FPGAs. My name is Frank Nelson. I'll be your instructor for this module. This module is about the architecture wizard and I/O planning functionality incorporated in the ISE software. This module introduces the architecture wizard, which is used to build your FPGA's clocking resources. This utility builds an instantiation for each customized DCM or MMCM component that you add to your design. This utility makes it easy to determine all the clocking features and select the options that you want in your design. It also provides error checking so that you don't build a component that will not work properly in your FPGA. This module also shows you the basics of the I/O planning functionality. The I/O planner is included with the ISE and the PlanAhead software. It is used to make pin assignments for your FPGA. It includes error checking and other features that assure that your pin assignments are effective and suitable to your device. You will also learn about the design aspects of making an effective pin layout. This module is a part of our Essentials of FPGA Design course. We recommend that you take the time to attend this course to learn all the critical design considerations you must make when targeting any FPGA device. After completing this module, you'll be able to list at least 2 uses for the architecture wizard, identify 2 features of the I/O planning functionality or the I/O planner, and be able to create high-quality pin assignments for your Xilinx FPGA. When you create a new design source with the ISE tools, it will ask you what kind of component you wish to make. You then select the IP core generator and architecture wizard and click Next. This will open the core generator, which allows you to add components by function or by component name. The core generator also contains other critical functions. It includes the Rocket I/O GTP and GTX wizards, which are used to build and customize serial I/O functionality in the Vertex 6 and Spartan 6 serial gigabit transceivers. Likewise, the memory interface generator is a part of the core generator also. This utility allows you to build and customize your memory controller for your system application. This tool enables you to build a custom memory controller for the Spartan 6 memory controller block as well. The most common use of the architecture wizard is to customize clock managers. This is done using the clocking wizard present in the architecture wizard's IP core list. The clocking wizard is an interactive graphical user interface, or GUI, that creates a clocking network based on design-specific needs. The required clock network parameters are gathered in a linear manner, which allows you to select only the desired parameters. Using the wizard, experienced users can explicitly configure the chosen clocking primitive, while less experienced users can let the wizard automatically determine the optimal primitive and configuration, based on the features required for their individual clocking network. The first thing you're going to do is select the inputs of the MMCM or DCM component you want. Select the primary input clock field in the first page. 1 input clock is the default behavior, but 2 input clocks can be chosen by selecting a secondary clock source. Only the timing parameters of the input clocks in their specified units are required. The wizard uses these parameters as needed to configure the output clocks that are desired. Now, we want to emphasize that this module is intended to give you an introduction to the flow of the architecture wizard, not teach you all the functionality of the DCM or the MMCM. So to learn more about these resources, make sure you review the features of the clocking networks from your chosen device's user guide. Secondly, you'll need to select the outputs of the clock manager you want. The number of required output clocks is user configurable depending on the functionality. The maximum number used depends upon the selected device and interactions with other major clocking features. You can input desired timing parameters such as frequency, phase, and duty cycle for each clock output. The clocking wizard will then configure the clocking primitive to comply exactly with the requested parameters. However, if this is not possible based on the available input clocks, then best attempt values will be provided and outlined. The wizard also allows you to specify how you want your generated clock signals to be routed in the FPGA by selecting an appropriate clock buffer setting. From this GUI, you can select whether a global buffer is to be used for routing the clock internally or whether another type of buffer, such as a regional clock buffer or buff-R, is to be used. While most designs will benefit most from being routed globally, routing local control or low fan-out control signals on regional buffers will maximize the use of the global routing resources and save power consumption in your application. The benefit of the global buffer is that it will help compensate for your skew. It is effectively a big fat wire. The buffer will also reduce your clock skew, but is designed for local clocks and less skew. You also have the ability to customize how the feedback of the output clock is routed to the input of the selected MMCM. This is important if you want to generate multiple clocks that are derived from the same MMCM and need to be synchronized. After you've customized your MMCM, the attributes made by the core generator are reported back to you. You don't actually have to do anything with these attributes, but they are reported and included with the instantiation of the component you created. This is helpful in case you decide to place your attributes directly in your design's UCF file. The UCF stands for User Constraints File and is a repository for all Xilinx-specific attributes. This includes pin assignments, timing constraints, and design attributes. So after generating your core, all generated attributes will be automatically added to your design and will be shown in your design's hierarchy. Likewise, you'll see a reference to the component's .xco file, which is a Xilinx proprietary netlist format. This netlist will contain any DCM, PLL, and buffer primitives that are specified by the Clocking Wizard utility. The I/O Planner is the pin assignment editor for the ISE and the PlanAhead software. PlanAhead also has a design analysis and floor planning functionality, but we're going to limit our discussions to just the I/O Planner for now. If you'd like to learn more about PlanAhead, we offer a course on all of its functionality. To start the I/O Planner, you click on the pin planning option before or after synthesis as shown in the Processes window. Generally, designers are planning their pins even before synthesis to ensure their board layout is effective, and of course the performance is not negatively impacted by making poor pin assignments. The I/O Planner checks that your pin assignments follow the I/O banking rules. These banking rules must be followed since each I/O bank is powered by a VREF and VCCO pin. The VREF powers all the input pins in the entire I/O bank, and since each input pin requires a different power voltage, this rule assures that all the input I/O standards have the same VREF. Likewise, each output pin in a bank shares the same VCCO, and the banking rules require this voltage to be compatible. There is also a noise analysis utility incorporated with the I/O Planner. This is used to make certain that each of the I/O banks and their associated pins do not run the risk of creating a ground bounce problem. This can sometimes occur if you exceed the device specifications for the maximum number of I/O pins per I/O standard in a bank. The noise analysis tool is disabled when launched from ISE. I can be fully utilized when an I/O pin planning project created in the standalone version of PlanAhead is used. Keep in mind that the noise analysis is not a complete ground bounce check because, of course, whether you have a ground bounce problem will depend greatly on the operation of your circuit and if multiple pins will end up transitioning at one time. Remember that the implementation tools also cannot anticipate this kind of problem. Unfortunately, that's always left to the designer to determine for themselves. The I/O Planner also makes certain that your pin assignments are appropriate for signals that are being routed to or from any of the dedicated hardware resources your design is using. All of this functionality is designed to help you avoid having to respin your board and resolve a pin layout problem later in the design flow. As I mentioned earlier, your pin assignments are stored in your user constraints file, which employs a user editable syntax. By having a single text file to hold all of your pin attributes and constraints in a single file, even when using PlanAhead, the overall FPGA design flow is simplified. So if you have not already opened this file, the next time you're running the tools, crack the UCF file open and try to get familiar with the basic syntax it uses. So as I mentioned, PlanAhead and the I/O Planner are included with the ISE software. The I/O Planner can be launched from the project Navigator. The I/O Planner supports making your pin assignments before synthesis or before implementation. This is important because most customers are locking their pins down before the HDL code has even been written. Now, the I/O Planner also includes a design rule checker that provides guidance for making pin assignments connected to reserved hardware, such as your serial gigabit transceivers or differential I/O pins. The I/O Planner also includes a unique fully automatic pin assignment functionality. Despite this feature being included, Xilinx recommends you place your timing critical pins first before allowing the remaining pins to be automatically assigned. The I/O Planner also supports grouping I/O pins when assigning them. This simplifies the management of your I/O interfaces. Now keep in mind that any pin assignments you make are not assuring high speed. They're built to help you get good performance by placing pins near the dedicated hardware. It is still possible to make pin assignments, and the implementation tools have little choice and are forced to place some route logic further from the pins than we like. This can be caused by poor HDL that creates timing critical paths, or a tight internal timing constraint that forces the internal paths to be considered a high priority. We will talk about pin layout recommendations in a few minutes, so hopefully those tips will help you meet your timing. On this slide we see the I/O planner has been opened and a design has been loaded. Note that no logic is highlighted in the device view, just the pins. That's because the HDL code has yet to be associated or synthesized with the project. However, the pins have been assigned, and we can see a number of the pins color-coded. To find a particular pin, we can scroll through the list in the I/O ports or package pins window. This window can display pins by I/O standard, alphabetically, or in other ways. But when I find the pin I want, I click on it and it becomes highlighted in the device view, package view, and the clock region windows. Likewise, the details of the pin's attributes are shown in the package pin properties box. This slide shows what happens when I select a pin from either viewer. When I click on it, it becomes highlighted in the device view, the package view, and the clock region windows. Likewise, the details of the pin's attributes are shown in the package pin properties box. From this functionality, you can easily understand the I/O banking relationship of your logic's placement in a clock region, shown on the left, with the associated I/O banks that each clock region has. In this example, the die view shows the logic associated with the clock region and the I/O banks associated with the same clock region. The package view on the right shows the I/O pins associated with that clock region's I/O bank, but shows them on a package view. The package view shows each bank with its own color, so it's easy to determine from the package view which pins are in which I/O bank. Likewise, power and ground pins are easily located by their color coding. The color coding is shown in the little column between the device view and the package view windows. The package view also allows you to see the predefined differential pairs on your device. The role of the device view and package view is pretty obvious, but the package pin properties box allows you to modify the associated pin attributes by modifying the associated text. So we can modify the location, slew rate, I/O standard, differential pairing, etc. with the text box rather than drag and drop it to whatever location we want. The different types of pins are also given their own shape, so that the available differential pairs are shown with a hexagon, and each is labeled so finding the associated pair is easy. Likewise, unused pins, that is VCC and ground pins, are all labeled and easily found. This slide shows some of the details of the package pin viewer. As I mentioned, it contains a lot of information. From this example, we can see that the pin name is shown with each assigned pin. In this example, an unused pin is left with just a charcoal-colored circle. In this case, the few used pins we see are given a brown square that contains the pin type, which can be an I/O, a VCC, ground, or another purpose pin. It also shows its location on the package, whether or not it's part of a differential pair, and in this case, an N type as part of the pair. It also shows the I/O bank that this pin is associated with, all in a text. Note that the I/O banks are color-coded, so bank 0 in this case has been given magenta or purple as its color. Likewise, note that each P and N pair can easily be found in the text with each pin. The power and ground pins are reserved and given a square with either a red or green color. You should also note from this example that VREF, or the reference voltage pins, serve as a dual-purpose pin with the I/O pins. Now this is easily seen by reading the text at the bottom of each pin's circle. You should also know that your final pin assignments can be exported into a CSV format for schematic symbol generation, placed into HDL, or put in UCF syntax. The UCF file can then be loaded into an Excel spreadsheet, and the pin properties can be cross-referenced by their attributes. Some designers find that very valuable. We have also seen from previous slides how cross-highlighting the pins is incorporated throughout the various windows of the I/O Planner. One of the other nice features of the I/O Planner is that importing existing pin assignments is supported by the tool. This means that if you are having a pin layout problem, you can still take advantage of the I/O Planner's functionality to help resolve your problem. And as I have already mentioned, noise analysis helps you to find pin assignments and I/O banks where you may have too many pins of the same I/O standard. This provides you some confidence that you're not creating a problem for yourself with your pin layout after you've done extensive design work. On this slide, we just wanted to show you how the I/O Planner allows you to run a design rule check on your design. To do this, you use the command Tools and then select Run DRC. As you can see, this will test your pin assignments on a number of levels, from the I/O banking rules to optimum placement relative to dedicated hardware. This screenshot shows a lengthy list that users can learn more about from the I/O Planner documentation. Likewise, the noise analysis is completed by using the command Tools, Run Noise Analysis. This will then let you customize your device parameters and board level parameters. When this is complete, a report is generated that will describe the status of each of your I/O banks in your design and whether or not you're going to have a noise problem. The I/O Planner also has a Pin Compatibility utility that allows you to facilitate the migration of a design between two density components that are supported within the same package. This is done when designers are testing their design on a prototyping board that supports a large density and then migrates to a smaller device for shipping. In this example, a Vertex 5 design is migrating between an LX330 density and an LX110 density, but is still using the same package. To facilitate the migration, the Pin Compatibility utility is called upon to prevent I/O pins from being used that are not an exact match between the two devices. This can be seen by the red X's shown in the package view in the I/O Planner. Likewise, all these incompatible pins are given a prohibit attribute which is stored in the UCF file and prevents the tools from using these pins during the implementation. Before we wrap up this module, we want to take a couple of minutes and talk about some of the necessary planning that designers must be sure to follow for their design's pin layout. Xilinx's newest FPGAs have a rectangular array of CLBs. Specifically, we're looking in this example as a Vertex 6 device. As the density of these devices increase, the number of rows increases by adding entire clock regions, so devices get taller, not wider. I/O pins are shown here in this example on the left and right edge. The center I/O banks contain all the dedicated clock input pins. This is because the device's DCMs and PLLs in this device are placed right next to this column, and they of course need access to input and output clocks as well as the feedback clock inputs. This column of I/O pins also contains the reserved configuration pins, and depending on your device family, there may be even some I/O pins in the center bank. You should also note that in the case of Vertex 6, as the density of the device grows, again extra I/O columns may be added. Spartan 6 family members have a very different I/O pin layout where all the pins are placed in a more traditional manner, meaning on the periphery of the device. The pins are distributed on the periphery and then likewise also placed on the top and bottom. There is a banking structure in Spartan 6, but there is no reserved column in the center of the die, so the user will have to evaluate the placement of their input clock pins when planning their design layout. We also want to emphasize that design layout usually transmits signals left to right or right to left along the FPGA, and very seldom do signals transmit vertically going up or down. This is because the bit ordering of the carry logic resources propagates the carry signal vertically upward. One of the most important concepts to remember about FPGAs is the carry logic resources propagate the carry signal vertically. This implies that the least significant bit be placed below the most significant bit and hopefully will follow bit ordering. This also must be followed for pin assignments. That way routing to or from associated logic that uses carry logic will have a minimal routing delay. In Spartan 6, we can also have I/O pins on the top or bottom of the device, but since carry logic is the same, designers should plan on assigning timing critical pins to the pins on the left and right edge of the die. This will shorten the associated routing delays and improve your I/O timing. You should also remember that the carry logic resources are inferred automatically by all synthesis tools, so you should plan your pin layout as I have just described. Likewise, recall that to reduce the chances of suffering a ground bounce problem, we need to manage how many pins we have for each I/O standard in each bank. The noise analysis tool included with the I/O Planner is your best means of analyzing the situation, but try to remember that dispersing at least some of your pins that may transition at the same time is always wise, so you'll have to plan that for yourself. This means that binary encoded logic and large data buses should be anticipated early in the planning process. Likewise, this may only mean breaking up a bus between two neighboring banks, but the sooner you plan for this, the less debugging you may have to do later on. So plan your pin out and use the noise utility very soon in the design flow. In this last slide, we just wanted to give you an example of bit ordering. In this case, two arithmetic functions have been inferred and will end up using carry logic. Since this propagates the carry signal vertically, the least significant bit needs to be beneath the next most significant bit, as we've shown here on the slide. Likewise, since we are combining the associated bits arithmetically, grouping the associated bits is also wise, since this will also shorten the writing delays for both buses and help assure good I/O timing. In summary, the architecture wizard consists of several wizards, including the clocking wizard, which we've spent a significant amount of time discussing, but also includes support for the 0 gigabit transceivers with the Rocket I/O wizard, as well as the memory interface generator utility for building your custom memory controllers. Now, these wizards make it easy for you to optimize your design to the dedicated resources in the FPGA. We also discussed extensively the I/O planning that you must encounter. The I/O Planner utility makes it easy for you to make good pin assignments that enhance your system speed and help you avoid common mistakes, such as avoiding ground bounce, following the I/O banking rules, as well as the I/O Planner includes a comprehensive DRZ check utility. Well, there are lots of places to learn more about FPGAs, and they all start at support.xilinx.com. To learn more about the architectured wizard, use the Help button in the dialog box. It really does not get any simpler than that. However, if your question has to do with silicon functionality, features, or limitations of the silicon, you should check out your device user guide. Each user guide contains a clocking resources and clocking management section. One of the best software manuals is the Synthesis and Simulation Design Guide that is available online as well. This provides general recommendations for coding practices, that is HDL coding practices, and also includes specific tips for coding for particular FPGAs. There's also the I/O Planner User Guide, which can be accessed from the Help menu in the ISE software or from the website. That's also very helpful for understanding the I/O planning capabilities. If you would like to see what other courses we offer or what other free videos are available to you, go to the Xilinx Education link you see here. I would also like to mention again that there are two basic FPGA architecture modules that discuss the basics of Xilinx's newest architectures, specifically Virtex 6 and Spartan 6. You may find these very useful, especially if you want to learn more about the device differences. But whatever you do, please take a second and let us know what you thought of this recording. Just click on the icon on the next page and tell us what you thought. Again, my name is Frank Nelson. You've been listening to the Architecture Wizard and I/O Planning training video. Thanks for listening, and thanks for your business.